Hello, everyone. So, this lecture continues on the discussion of inner product spaces, and we explain orthogonal projection, and we also explain some Gram-Schmidt procedure. What Gram-Schmidt procedure does is that if you're giving it some basis for your vector space, it gives you an orthonormal, nice-looking basis. We'll see in the orthogonal projection that having an orthonormal basis is actually very useful. There's also Cauchy-Schwarz inequality and triangle inequality that we don't get to discuss actually in this session, but our next session I'll explain that. I'll explain that. So, but I haven't forgotten that last session finished without proving one theorem, and the first thing to do is to prove that. Okay, so let's start. So the first thing we want to discuss in this session is theorem 9.10. We explained the theorem a bit, and we didn't prove this. Well, we basically proved the first part, but only for two vectors v1 and v2. Okay, let's see what it says. So we have an inner product space over C. We have one basis, which is an orthonormal basis. Okay, we are saying that for any v and w, any two vectors, we have the following properties. Okay, the first property is about only one vector. It writes v as a linear combination of vi. Okay, vi's are a basis, so that's the writing a linear combination is always possible. And that linear combination is always unique. Means that the coefficients that we find for vi are uniquely determined. Okay, so what this theorem is telling us extra, the information is providing us, is saying that the coefficients can be computed using this inner product. Okay, so let's prove this and then we look at the second part of the theorem. So V is equal to mu1, v1, etc., mu n, vn for some mu I in our field, okay? Because VI's are bases. So, so let's say there exists uh, mu i's such that this V is equal to uh, mu1 v1 till mu n v. Okay, so how can we calculate? So what actually we want to prove is that mu I is obtained by this inner product. Okay, so what is mu I? Okay, so let's just write this. If we take the inner product of vi and v, what do we get? We get just let's write the expression v and mu1 v1, etc., mu n vn. Okay, and instead of v, I just replaced this term. Okay, this would be equal to what? Because the inner product is linear with respect to second component, we can just expand this and write this as mu1 vi vi plus dots mu n v vn. Okay, so let's see. Let's also write mu and mu I actually in between, so we see that. So we just write this here, and okay. plus so mu I v I and vi plus. Okay, do you agree with this? I just wrote this expansion. Okay, what do we know about this basis? They are orthonormal, right? Orthonormal basis. So it means that vi and vj is equal to Kroneker's delta. That means it's equal to 1 and I is equal to j, and 0 when I is not equal to j. Okay, so if we just write this, all of these, this has to be 0 because I is not equal to j. So this is 0. All of them are 0 except when I is equal to j. So it means that this is the only thing which is I. So this is, so this part is 1, and this part, when you multiply the whole thing, is mu r. So when you take the inner product of vi with such a linear expansion, it kills everything except the vi there. Okay, so it gives us only mu I times 1, which is mu I. Okay, that's actually what we wanted to prove for this part. Let's see what the second part was saying. So it's the second part of the theorem was saying that if we take two vectors, v and w, okay, in our space, we can write this as vi and v conjugate and vi w without conjugate and I from 1 to n. Okay, so the inner product of two vectors is a number. The left-hand side is a number. The right-hand side also is sum of some inner products multiplied, etc. So both hand sides are numbers. Okay, so actually let's elaborate on the left-hand side a bit. Assume if v is equal to mu 1 v1 mu n vn. If we have w equal to some other, let's write eta 1 v1 plus eta n vn, because vi is our basis, right? We can write, we can find some coefficients that these expressions are true. Okay, so then v, the inner product with w, would be equal to what? Would be equal to this expression that we have written here. So, okay, the inner products of this with inner products of this. Okay, I wanted to duplicate. Okay, so we can multiply this. Nice. As also we have explained this before, this is linear with respect to the second component. So this must, so, and then it's anti-linear. Basically, the only difference between the second component and first component is that when you have coefficients in the second component, you take them out without any change. But in the first component, when you take them out, you get a conjugation. Okay, so if you multiply this, you will get mu. Let's write a few terms to, it's actually to see what's happening. So we'll get, so this expression, whatever it is, it's here. And eta 1 v1 plus that expression that we have here, mu1 v1 plus mu n vn, times eta n vn. Okay, so if we expand this, would give us mu n, eta 1, sorry, mu 1 v1 plus mu n vn, the inner product with v1, plus eta n, the same thing, vn. Okay, let's look into this a bit more. And so vi is multiplied to this sum. It kills everything except the vi term. Okay, so because it's an orthonormal basis. So this would be equal to eta 1. So basically, if I take these out and write it as linear combination, we get mu1 conjugate, mu1 conjugate, and times v1 and v1 plus etc. mu and v and okay. So plus all of these eta n, and I write the last term similarly, mu 1 v1 vn. Okay, then vn and vn. Okay, I'm just writing so much details, but this would be equal to, okay, all of these terms are killed except when vi is equal to vj. Okay, so when this, only this term remains. From here, only this term remains. Okay, so we get eta 1 mu1 plus eta n mu n. Okay, I'm actually missing writing mu n bar here. Mu bar here. So this is the equality, and then, well, from 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 I, we know that mu I is equal to vi and v. So the coefficients of v, basically in terms of vi were given as mu I, and then lambda I, sorry, the eta I are the coefficients of vi or the coefficients of w. So can we find those? Okay, so that's all we want. Okay. The last part of the theorem is saying that the norm of v is equal to the sum I equal to 1 to n of the modulo of v1 v this squared square root. Okay, so just let's write the definition and what it gives us. So the definition is the norm is V, the inner product with itself, the square root. Okay, and so here let's just expand. So from part two, this is equal to mm, so we put the coefficients of the first vector with this, it conjugates, and then we put the vi and with the second vector, which is also v here. In the previous part, it was w. So, and we add all these, I equal to 1 to n. Okay, so this is what this is vi v absolute value, because these are some complex numbers. When we multiply them to their conjugate, we get their absolute value. Okay, so the rest we have to just write what's remaining. Okay, so actually this is equal to 1/2, right? And so inside the parentheses, what are so projection itself is was a concept in chapter 7 that we skipped, and the main object of study today are the orthogonal projections. So let's first see what projections are, and I explain why I have put this photo here. Okay, so definition basically, by, well, yeah, 7.58 is saying that when you have a linear map, linear, P is called projection. P is called projection. If P squared is equal to P. What does it mean, P squared? We mean that P OP is equal to. Okay, it means that if we apply P on any vector 2 times is the same as we apply it once. Okay, so let's prove one property of this. For example, if P is a projection and we take one element in the image of W, in image of P, then P of W is equal to W itself. How do we prove this? Because in the image, therefore, there exists V in, so V, P is from V to V, in V such that W is P of V. Okay, so what is, we are trying to get more information about P of W. Let's calculate. Okay, P of W is P of V, and this is equal to, by the properties of the projection, applying something 2 times, this projection 2 times is equal to applying once to one vector. And okay, so we just got that PV, just W. Okay, so we just proved their remark. Another remark is that, so let's put this one. Okay, if we have any vector V in V. So V minus V oh, is in the kernel of P. Okay. For any vector, if we write V minus PV, that would be in the kernel. How do we check this? So let's just apply P to this vector and see if it's becoming 0. Okay, because P is linear, we can write PV minus P squared V. Okay, and these are equal because of the property of the projection. So this is okay, nice. So we saw two small facts about this. So this picture, what I want to say is that taking a photo is like a projection. It's actually a linear map when you take a photo, because if you have addition of two vectors, and if you look at the image, you get addition of these two vectors, right? The addition here is mapped actually to the addition of two vector in the photo, but also if you multiply some vector to some number, here is also in the image is multiplied, okay? That's why the images don't look distorted. And another property for taking photo, if the resolution is not lost, is if you take a photo of a photo, let's say you take a photo from this screen, if the resolution is not lost, is you get the same picture as your photo. Okay. Taking a photo is the same as taking a photo from a photo. Okay, so taking a photo is a projection. So we have finally arrived to the main notion that we want to talk about today, orthogonal projection. So we have V an inner product space, and P from V to V is a linear. So, so P is called an orthogonal projection. So let's say if it's a projection, it has this strange property, PV U, that V PU. These two are equal for any V and U in V. Then P, then P is called an orthogonal projection. So this doesn't seem actually very intuitive, and but let's explain the geometry of it. What do we expect from an orthogonal projection? Orthogonal projection is what we expect for an object. Let's say V is a vector here. Orthogonal projection is the shadow of that vector when sun is at its zenith. So we have PV, and here we have some orthogonality perpendicular. Okay, so what's this vector here? Let's write it. So there is that vector that if I add PV plus that vector gives me V. So what's that vector? It's V minus PV. Okay, so PV is the vector which is the shadow or the projection is such that we want this bit of the vector, this thing, to be perpendicular to any vector W in W. Okay, so W is given a subspace, okay, orthogonal projection onto W means that a map that actually gives these shadows PV such that the orthogonal part is perpendicular to every basically vector in W. And that's what the intuitively what we are looking for. Okay, so we can basically therefore see that there are, we have said one formal definition, which is definition 911, and I have said that this intuitive definition, that if we have a projection such that this property holds, V minus PV and W is equal to 0 for any V in the image of P. Okay, so it's important to understand that these two notions are equivalent. I explained why Y implies 2. So I'm saying that these two properties actually imply these two properties. Let's write. We have these two properties for definition 1, definition 911. Okay, so if what we want to prove is V minus PV and W is equal to 0 for any W in W. Okay, but we can write this V minus PV W equal PW. Okay, why? Because W is in the image of P. Okay, then P of W is equal to W. That's the property of the projections that we just proved. And so if we expand this, or okay, let's use the second property. We can take this over here, right? And because of the definition, this property holds for P, so we can do that, and then we can write P of V minus PV and PW. So I'm not being very consistent with putting parentheses or not, but well, sorry about that, but it's not much of a difficulty. So, so we have PV minus P squared V, right? And PW. And this is equal to, because P is a projection, P squared of any vector is equal to P of that vector. So this is 0, and this is P of, okay, when P jumped over here, of course, this meant that this we have to erase PW, but it wasn't wrong because P of W is actually equal to W. And let's do this. But so anyways, we get W here and we get 0 because multiplication of the 0 vector to inner product of any the 0 vector to any vector is 0. Okay, so we just show that. We have just shown that this property holds. Okay, so this, in at least the formal definition implies the intuitive definition, which is good. You can see the converse easily as well. Let us now discuss proposition 912. It's a very, very important proposition. So it's saying that V is an inner product and inner product space, and we have W a subspace. We consider W1 till Wk an orthonormal basis for W. Then this map that we are defining, PW, that such that for any vector is given by multiplication of wi and wi, so I equal to 1 till k, is an orthonormal projection. Okay, so what it's saying is that we are given this map and we want to show that it's also orthogonal projection. So how do we, what should we prove? We have to prove that p squared is equal to p, and p, okay, we have p of w, p of w of v and u is equal to v and p w of u. Okay, so let's just see these properties. So let's put this 1, 2. Following the notes, it's actually easier to first see 2 and then use that to prove 1. Okay, so let's just write it. We want to see P W of V, P W of V. Okay, so I want to basically plug in P W of V. Okay, so it's W I V I U I. Okay, so if we expand this, I K, this is the expression which is given for PW of V. And then I just plugged in here. And when we can expand this, so what we remember from this inner products, if we have one linear combinations in the first component, the coefficients get conjugated if we take them out. Okay, so this would be equal to sigma I equal k, 1 to k, so W I V and then W I U. So there is a mistake here, and now it's fixed. Okay, so don't forget the conjugation in the first, coefficients in the first component. Okay, let's also calculate P V and PW of U. Okay, so I just plug in again. So it would be V and PW of U is equal to sigma WIU and WI. I equal to 1 to K. And then let's expand this. Okay, so in the second component, it's linear. So if we take out the coefficients, actually, we don't have to put the conjugation. We don't put the conjugation. So this is equal to the sigma I from 1 to K, V, and okay, these are the coefficients which will go out. Let's write them first. So the WI and U, and so this basically multiplied to this VWI. Okay, so this is what we get. So what are we looking for? We wanted to show that this thing is equal to this thing. The first one is equal to, turns out equal to this. The second part is equal to that. Okay, just let's compare this. We have this in both of them, but also we have WI inner product with V conjugates Okay, here we have V and WI. So the order is changed, but we get a conjugation. So these are equal. So we have this we let's put one, this I equal to this. The second property that we have to prove is this that PW is an orthogonal projection. So it's a projection too. So we have to prove that P is equal to. And so if we have PW squared of some vector, we want to calculate that this is actually equal to PW of V. So let's just plug in and see what we find. So PW of sigma and WI and V, okay, and we have WI, I equal to 1 to K. This is equal to, well, this is a linear map, so of course this will go out, so we have sigma of I, 1K, PW, okay, sorry, okay. So we have the sigma, P, the coefficients are WV and PW of I, and this is equal to WI and V, WI. Again, this is equal to this thing. So let's say Y PW of W is equal to, because just calculate this. PW of W is equal to, by definition, you write WI, and okay, let's put this J so that the indices are not confused. So WI, WJ, J equal to 1 till K, and this is equal to what? This is an orthonormal basis, means that when I and J are equal, then this is 1. When they are different, this is 0. So basically, everything vanishes except when they are equal, and then what we get would be I and I. That's the only thing that remains, WI, and this is 1, so we get WI. Okay, so we prove both parts of the implication. So what we see is that this map, which is given in this way, is an orthogonal projection. So we discuss this map a bit more. So let's look at this formula in when k is equal to 2, when we are given two orthonormal vectors, and we look at the span W, which is the span of W1 and W2. And here we want to find basically the orthogonal projection of any vector onto W. And this formula is just telling us how to find a formula. So for any subspace of any dimension, the formula is telling us that if you have one orthonormal basis, then you have the projection formula. This is very useful in practical problems, and I explain a bit actually in the next session. Also, it's important to also focus with the case on the case where k is equal to 1. That means that W is a span of one vector. That vector has norm 1. Okay, so we want to look at V and find this PW of V. The formula is just telling us that to find that, actually we take the inner product of the normal vector, the vector which has norm 1, and with our given vector V. So we take this number and we multiply it to W naught. Or and consider the inner product given by the usual dot product. We have this formula that gives us the relation between angle between two vectors. So we have V and W naught, and the angle between them is phi. With this inner product, which is dot product, we have this formula in, and that gives us cosine of phi. And we know that the projection of V onto W is just this vector. Okay, how do we calculate such a vector? We just multiply the norm of V to cosine of phi. Okay, but this gives us the length of the vector we are after, and we have to multiply it to the normal vector W naught. Okay, so this is equal to, just let's replace cosine in this formula here into here. So that gives us W naught, of course, V, normal V with this V, normal V in the denominator cancel, and then we have W naught. So basically, this is the projection formula that I was mentioning is what we were already using with cosine.